Hello, welcome back. In this video, we'll discuss the soft and hard magnetic materials. We have seen the hysteresis of a ferromagnetic material. The hysteresis has a connection with the energy losses in a magnetic material. If the area is more under the hysteresis loop, it means higher will be the losses in the process of magnetization and demagnetization. Similarly, if the area under the hysteresis loop is small, then smaller will be the losses in the magnetization and the demagnetization process. In order to understand these losses, we shall look into a theory that is used to explain the magnetism, which is known as Weiss domain theory. This is the hysteresis loop. In this diagram, there are two portions. This portion corresponds to the unmagnetized ferromagnetic sample, and this is a magnetized ferromagnetic specimen. The ferromagnetic materials, though spontaneously magnetized, do not show macroscopically observable magnetization, and the magnetization is explained using the Weiss theory of ferromagnetic domain. According to this hypothesis, the entire ferromagnetic volume splits up into a large number of small regions of spontaneous magnetization. The regions are called the domains. Each of these regions is called as a domain. These domains are separated by domain walls. Each domain is at all times spontaneously magnetized to saturation and has a definite magnetic moment. In the absence of an external magnetic field, the magnetic moment vector of the separate domains are oriented in all possible directions the way they are shown here. As a result, the net magnetic moment of the entire body equals to 0. When such an unmagnetized ferromagnetic sample is placed in an external magnetic field, then these domains, they orient in the field direction. You see the magnetization vectors are aligning in the field direction. Say this is the field direction. Similarly, one can also notice that the size of the domains also is altered. Here we have small domains, whereas here two large domains along this side. The domains are changing their orientation and their size. Because of these variations in the changes in size, we get what is known as the hysteresis loss. When a ferromagnetic specimen is magnetized by keeping it in an external magnetic field, those domains in this specimen that are favorably oriented with respect to the external field, they grow in size the way it is shown here. And also each domain rotates as a single unit such that its direction of magnetization becomes aligned with the applied field. In the process of increasing the size of the domain and in rotating the domains, certain amount of energy is consumed. Now when the external magnetic field is removed, the domain boundaries do not move back to their original position, and the specimen is left with some magnetization. It means that the energy supplied to the specimen during the magnetization is not fully recovered upon removing the external magnetic field. The difference of energy is lost as heat in the material, and this is known as the hysteresis loss. And depending on the area under the hysteresis loop, the hysteresis loss also change. If the area under the hysteresis loop is small, then smaller will be the hysteresis losses. Similarly, when the area under the hysteresis loop is large, higher will be the hysteresis losses. Basing on the area under the hysteresis loops, the magnetic materials are classified into two. They are soft and hard magnetic materials. The soft magnetic materials are those magnetic materials which are easily magnetized and demagnetized. Such materials are called as soft magnetic materials. The magnetic materials and demagnetized are known as soft magnetic materials. The soft magnetic materials are characterized by a thin hysteresis loop. and it is essential for a material to be called as a soft magnetic material. The material should have a high initial permeability and a low coercivity. Here you see the hysteresis loop. The hysteresis loop looks almost like a thick line in this fashion. So the coercivity is small. Here you see on either sides the coercivity is small, and the area under the loop is also small. So if the area under the loop is small means permeability is high. The intersections along the h-axis are small means the coercivity is low. Because of these two factors, the material reaches saturation magnetization with a relatively low applied field. Since the area is low, low hysteresis energy losses. Its saturation magnetization is low. Means for the relatively low applied field, these materials they reach the saturation magnetization, and further these materials they exhibit low hysteresis losses. Low hysteresis losses is an important parameter. These materials have very small area under the hysteresis loop. Since the area of the hysteresis loop represents the energy lost as heat during a cycle of magnetization, smaller the area, lower are the power losses, and the greater the possibility of using the material at higher frequencies. A low value of coercivity corresponds to the easy movement of the domains. We have seen here low value for the coercivity. This corresponds to the easy movement of the domain walls. There is yet another mechanism that is used to explain for the losses in the magnetic materials. When the magnetic flux through a conducting material changes, voltages are induced, because of which the eddy currents will be present or induced, giving rise to eddy currents. Eddy currents are the surface currents. In these surface currents, they also cause a loss in the energy, which means there are two different possible mechanisms to explain the losses in the soft magnetic materials. One is the hysteresis losses, the other one is the losses due to the eddy currents. In order to minimize the losses due to the eddy currents, the materials have to be modified to have higher resistivity. A material with a higher resistivity will conduct less. As a result, losses due to the eddy currents can be minimized. We shall now look at the applications of soft magnetic materials. Since the soft magnetic materials can be magnetized and demagnetized very quickly, they can be used in electrical engineering, such as core of transformers, motors, etc. Examples: pure iron with small carbon content and silicon iron alloy. Now we shall look at the hard magnetic materials. The hard magnetic materials are those materials which have a high resistance to demagnetization, a high remanence, high permeability, a high coercive field, and a large hysteresis loop characterize the hard magnetic materials. The hard magnetic materials are those which have a high resistance to demagnetization, a high remanence, high permeability, a high coercive field, and a large area under the hysteresis loop. The hysteresis loop of a hard magnet looks like this. Here, the indigo line represents the ideal hard magnet and the line in blue represents the real hard magnet. One can see that the magnetization increases quite sharply and the demagnetization is slow up to some point. Beyond that, it suddenly drops to zero. Area under the curve is quite large and the coercivity is high because the intersections are here and here they are separated by a significant amount of the H field. The hard magnetic materials are magnetized in a magnetic field strong enough to orient the magnetic movements of their domains in the direction of the applied field. Part of the energy of the applied field is converted into the potential energy, which is stored in the permanent magnet produced. A permanent magnet in the fully magnetized condition is thus a relatively high state as compared to a demagnetized state. The power or external energy of a hard magnetic material is directly related to the size of the hysteresis loop. The magnetic potential of the material is measured by the energy product BH max. The applications of hard magnetic materials are: they are used in loudspeakers, medical applications such as MRI, where permanent magnets are used. Examples for hard magnetic materials are ferrites, alnico, and cobalt, platinum, etc. In this video, we have tried to understand the soft and hard magnetic materials. Before understanding the soft and hard magnetic materials, we have discussed the ferromagnetic domain theory briefly. The magnetic materials which are easily magnetized and demagnetized are known as soft magnetic materials. These materials should have a high initial permeability and a low coercivity, and its saturation magnetization is low, and they exhibit low hysteresis losses. The area under the hysteresis loop also is small. Because of the small coercivity, easy movement of domain walls is required in the case of soft magnetic materials. There are two different mechanisms using which the losses in soft magnetic materials can be explained. The first one is the hysteresis losses. The second one is losses due to the eddy currents. The eddy current losses will occur because when the magnetic flux through a conducting material changes, voltages are induced, and these voltages they give rise to the eddy currents or the surface currents. Because of these surface currents, there can be a loss which is also known as µ-claz. Because of the surface currents, energy is lost in the form of heat. So this is the second major contributor for the losses in magnetic materials. The applications of the soft magnetic materials are: they are extensively used in electrical engineering, such as in manufacturing the core of a transformer or a motor, etc. Examples for the soft magnetic material are pure iron with carbon content and silicon iron alloy. These are the two examples. Later we have seen the hard magnetic materials. The hard magnetic materials are those which have a high resistance to demagnetization, a high remanence, high permeability, a high coercive field, and a large hysteresis loop. We have seen the hysteresis curve of a hard magnetic material. Applications of the hard magnetic materials are loudspeakers, MRI, etc. Examples for the hard magnetic materials are ferrites, alnico, and cobalt, platinum. Thank you.